Hey, here's the video for the solutions to the Chapter 3 solo test. We started off with a couple of synthetic division problems using the remainder theorem, which says that when you use synthetic division and you get a remainder, that remainder is actually the value of the function for that x value. So if you want to find p of -2, just use -2 as your divisor in your synthetic division. That remainder is p of -2. So we get -95 in part A, and we do the same thing for part B using 5 as the divisor. Remember, there is no x cubed and no x term, so you have to use a 0 in those spots for your dividend in the synthetic division process, and you end up with p of 5 equals 850. All right, next problem, multiplying a couple of complex binomials together. They're complex numbers in a plus bi form. We talked about this a lot in class. The issue really is when you multiply I root 2 times negative I root 2, you get negative I squared times root 2 squared, which is just 2. So that whole thing right there, because I squared equals -1, this is -1, 2, that makes positive 2, which you combine with a 3 to get 5. And then minus 2i root 2. 5 minus 2i root 2. And if I was to ask you on the test to identify the value of b, for example, in this number, you would say that b equals -2 root 2, because that's the number that's multiplying I. Over here, when we have a fraction with a complex denominator, we use the conjugate of that denominator over itself. So we have a fraction equaling 1. We multiply that fraction times our beginning fraction here. And this gives us a whole number in the denominator of this fraction. Remember, it's a squared plus b squared. And since b is a 1, that's 64 plus 1 makes 65. So we got 32 plus 4i. That's just 4 times 8 plus i. 32 plus 4i over 65. And again, if I was to ask you what the value of b is, the value of a, let's do in this equation, in this number, that would be 32 over 65. Okay, so a plus bi form, very important to keep it in that form. Let's do the next problem. These true or false questions, great deal of discussion about this in class today. I'll try to make this as brief as possible. It is every polynomial function of an odd degree has at least one real root because it has to cross the x-axis at least one time. One end's going up and the other end's going down on an odd degree polynomial, so it has to cross the x-axis at least once. A fourth degree polynomial cannot have exactly 3 real roots. That's not a true statement because if it had exactly 3 real roots, since it's a fourth degree, it would have to have one more root, and that would have to be imaginary, and imaginary roots only come in conjugate pairs. So the thing that makes this statement untrue is that it is impossible to have exactly one complex root. Complex roots always come in even numbers, 0 or 2 or 4 or something like that. The issue behind statement 3, it's not a very good statement, I'm sorry, I apologize for that. The x-intercepts of a polynomial function are not necessarily the same as its roots, and that's sort of getting at the same idea here. That is, as I wrote it, a true statement in my mind anyway, but you could sort of argue it because it's kind of it's a poorly constructed statement. But the idea is that x-intercepts represent real roots. You can have imaginary roots that aren't represented by x-intercepts of the graph. That's kind of the main truth behind that statement. Maybe a clumsy way of getting at it. A fifth degree polynomial has at most 5 x-intercepts. That's true. It could have less than 5 x-intercepts, but it certainly could not have any more. And the number of x-intercepts of a polynomial is always equal to its degree. Nope, sorry, that's not true. If the degree is, let's say, 4, but 2 of those 4 zeros are imaginary, then you're only going to have 2 x-intercepts. And other situations are possible as well. So that is not true. All right, let's look at finding the factors. Remember, if you know what the zeros are, you know what the factors are. And that's kind of one of the points that we're getting at. In fact, we're kind of coming back around to this practice of factoring polynomials, which we started with in this practice. So if you find the zeros of x squared plus 36, you end up getting x equals plus or minus 6i. That's not the factors, that's the zeros. So the factors are x minus 6i and x plus 6i. Same idea over here. If you find the zeros of x squared minus 5, that's going to give you x squared equals 5, so x equals plus or minus the square root of 5. Those aren't the factors, those are the zeros. So the factors are x plus root 5 and x minus root 5. Let's do one more. This one, you got to use synthetic division. Oh my gosh! To find the zeros of this here polynomial. It turns out that this polynomial is x plus 1 cubed. In other words, the zeros of this are all the same number. There are 3 of them, but they are all identical. The zeros are negative 1, and we can factor that to x plus 1 times x plus 1 times x plus 1, or simply x plus 1 cubed. Okay, let's do the, end behavior problems here. Since this ends up being a 4th degree, because we've got a 1st degree term and a 3rd degree term multiplied together, we get 4th degree, but this term right here has 1 minus x. So that means that x is it's got a negative coefficient right here, and when you multiply that out, you're going to have a negative coefficient overall, and that means it's upside, that is, both ends are pointing down. Both ends go in the same direction because the degree is even, and since that coefficient for x is negative, they're going down. Let's look at the other one. This one's a little bit simpler. This is a positive lead coefficient with an odd degree, so that means ends are going opposite directions, and since it's positive, the right end goes up and the left end goes down. Let's do the backside. Here's our asymptotes and intercepts for these functions here. All right, try to make this quick. The x-intercept is where y equals 0, okay? And if y equals 0 for this fraction here, that means the whole fraction must equal 0, which means that the numerator must equal 0. So the x-intercept is where the numerator equals 0, or in other words, the zeros of the numerator. And when you work that out, you get x equals 3 for the 0, and so the x-intercept is at 3. Y-intercept is where x equals 0. So when you replace x here and here with 0, you get negative 9 over 2. So our y-intercept is negative 9 halves. Our vertical asymptote is where the denominator equals 0. So that's negative 2. So x equals negative 2 is the vertical asymptote. The horizontal asymptote is at y equals 3 because these two polynomials, top and the bottom of this fraction, have the same degree. And when that happens, you just look at the lead coefficients of the top and the bottom, and the horizontal asymptote is the ratio of the lead coefficients. So that would be 3 over 1. There you go, y equals 3. We don't have a slanted asymptote in this function because the degree of the top and the bottom are the same number. Let's look at this one here. The next one has a 0 degree polynomial, which is just a constant number on top. All right, so the x-intercepts of this function, well, there aren't any because this fraction will never equal 0. Top always equals 5, so it never equals 0. So no x-intercept. The y-intercept, however, when you replace x with 0, 0 there, 0 there, you still got a 5 on top, and that's 5 over 2, so the y-intercept is 5 halves. The vertical asymptotes for this function occur at the zeros of the denominator, which, when you factor the denominator in order to find the zeros, I don't know why I put a 1 there, that's not true, it should be a 0. Where did I go? There you are, sorry. The zeros are negative 2 and negative 1. So x equals negative 2 and x equals negative 1 are the vertical asymptotes. All right? The horizontal asymptote, since the degree on the bottom is greater than the degree on the top, this fraction's horizontal asymptote, this function's horizontal asymptote is y equals 0. All right? When the degree is greater on the bottom than the top, the horizontal asymptote equals 0. So that's our y equals 0 is our horizontal asymptote. And once again, it does not have a slanted asymptote. Well, let's keep going. One more. Let's find the x-intercepts of this rational function, which once again are the zeros of the numerator. Okay, well, this was fun to factor this one. 2x minus 3 times x plus 3 are the factors of that numerator. That means the zeros are positive 3 halves and negative 3. Therefore, those are our x-intercepts across the x-axis 2 times. The y-intercept is where x equals 0. So 0, 0, 0. Put in 0 all those places. You end up with negative 9 over negative 3. That means our y-intercept is positive 3. There it is, positive 3. The vertical asymptote for this function is where the denominator equals 0, and that would be at positive 3. So x equals 3 is our vertical asymptote. Our horizontal asymptote, well, gosh, this one doesn't have a horizontal asymptote because the degree on top is greater than the degree on the bottom. So no horizontal asymptote. However, the difference between the degree on the top and the bottom is 1. This is a second degree, this is a first degree. So when the difference between the degrees there is 1, that means we have a slanted asymptote. So we find it just by doing the division, the long division for this polynomial. So 2x squared plus 3x minus 9 divided by x minus 3. I'm using long division just for the heck of it. You could use synthetic division in this case, but it's a little confusing, to be honest with you, when you do that. Anyway, you do this division, you end up with 2x plus 9 as your quotient for that division. Therefore, y equals 2x plus 9 is our slanted asymptote. And to finish this thing up, I'm just going to give you the zeros here. I'm not going to go through the whole guess and check process of using synthetic division and the rational zeros theorem, factors of this divided by factors of that, working all that out. We get these numbers here for our zeros, and unfortunately I must have had a typo on my third problem there. It doesn't have any rational zeros. It's a bad problem. Grr. And so don't worry about that one. Okay, there's our solutions. Enjoy. Bye-bye.